morning to all my dear viewers. Today I like to discuss the kinetics of second order reactions part 2. Before that, I give some correction which I have made a mistake in part 1, and this corrections number 1. Correction number 1, and here it is, I have written not equal to B, but it would be concentration of A not equal to concentration of B naught. Naught is omitted. And the second correction, whenever plotted using this equation to find out the value of K2 rate constant of this reaction, these corrections are made for the part 1 of this topic. And here it is A naught minus A divided by A naught into A. Here T, here it is 0, and it will pass to the straight line. In my first part 1, I have omitted this term, and this term have been included here. So correction is made. Now I am coming to the kinetics of the second order reactions part 2, where A initial concentrations of the two reactants are not equal. Let the reaction is A plus B, and giving this P. A and B, these are the two substances, and so it is a second order reactions since its rate is proportional to two concentration terms. Proportional to two concentration terms, so second order. And say when T equal to 0, it is concentration of A naught, and it is concentration of B naught, and it is 0, and the concentration of A naught not equal to concentration of B naught. We shall discuss whenever the two percentages are different for the two substances, and what will be the differential rate equation, what will be the integrated rate equation, how the rate constant K2 could be determined, and one example. So the rate of this reaction, first one, the differential rate equation. Differential rate equations of this reaction minus dA by dt equal to K2, and concentration of A and concentration of B, two concentration terms. So it is second order reactions. K2 is the rate constant, which is very important term for this reaction. It remains constant at a given temperature. And volume of the reaction mixture have also been kept constant, so that the change in whenever the reaction is going on, the change of these mole numbers does not affect the volume. If volume is being not constant, then the concentration will change. So this is the differential form, and say let it 1. Let this equation 1. Now we have to find out the integral integral or integrated rate equation. Integrated rate equation. This has been formulated by the following way. First, I have to do the separation of variables. Say minus the concentration of A divided by concentration of A, concentration of B equal to K2 and dt. This is the separation of variables. When T is being changed, concentration of A and B, they are also changed. These two are the concentrations of A and B which remain unreacted in this reaction vessel. So this is the two variable terms. We have to replace this one variable in terms of this other variable. So since these two A and B are reacting 1:1 mole ratio, so the number of mole A number of mole A reacting with the same number of mole of this reactant B. So concentration condition is that A naught minus A equal to concentration of B naught minus B. This is the initial concentration. These two are the initial concentrations. Zero subscript have been given for the time 0, and this one is the mole of A reacting, and this is mole of B reacting. Since A and B are combining 1:1 mole ratio, so these two are the same. So instead of B could be replaced as B naught minus A naught plus concentration of A. This is the equation number 2. So this B is replaced by right hand side. So minus concentration A concentration divided by A into concentration of B naught minus concentration of A naught plus concentration of A and bracket close equal to K2 dt. Now the B's concentration term, B of concentration is replaced by in terms of the concentration of A. So right hand side T variable, left hand side A variable only. So this term, this product, this could be split into the two terms. This, or we can write the minus 1 by concentration of B naught minus concentration of A naught, if we write this one before this one, and it will give you B concentration of A divided by concentration of A and minus B concentration of A divided by concentration of B naught minus concentration of A naught plus concentration of A equal to K2 dt. Now, if I omit this minus sign, then this will come here and this will go there. So, or 1 by concentration of A naught minus concentration of B naught within bracket, and you do the integration. Here it is integrated, here it is integrated, and here also integrated. K2 is constant, we go outside of this integral sign. So if we do the integration, this is a definite indefinite integral, so this will give you ln a dx by x ln x minus ln and concentration of B naught minus concentration of A naught plus concentration of A bracket close equal to K2T plus IC. IC the integration constant. Integration constant. Now we have to evaluate the integration constant value by putting this condition. The condition is that for the evaluation of integration constant at t equal to 0, concentration of A equal to concentration of A naught and concentration of B equal to concentration of B naught. B naught. So putting these values here, 1 by concentration of A naught minus concentration of B naught bracket close, and here you can write this ln concentration of A divided by log A minus log B. So here it is concentration of B naught minus concentration of A naught and plus concentration of A, and it is within this bracket, and here when t equal to 0, A equal to A naught, and this is also A naught, equal to K2 into 0 plus IC. When t equal to 0, this A will be A naught and A will be A naught. So A naught cancel, and this one, so the value of IC, so value of IC 1 by concentration of A naught minus concentration of B naught within the bracket and ln concentration of A naught by concentration of B naught equal to K2 equal to 0 equal to 0. So the integrated rate equation. So 1 by concentration of A naught minus concentration of B naught bracket close ln concentration of A divided by concentration of B naught minus concentration of A naught plus concentration of A equal to K2T plus 1 by concentration of A naught minus concentration of B naught into ln A naught by B naught. So putting this value of IC, we get this rate equation. If we multiply both A naught minus B naught, then the integrated rate equation will be ln concentration of A divided by concentration of B naught minus A naught plus concentration of A equal to K2 into concentration of A naught minus concentration of B naught bracket close into T plus ln concentration of A naught by concentration of B naught. So this is the integrated rate equation. Now third part, evaluation of K2, rate constant of this reaction. For the evaluation of K2, we have to do some kinetic experiments. Means at different time intervals, we have to determine the value of A, means concentration of A remaining at time t at different time intervals, either by physical method or by chemical method. So by determining the concentration of A at different time intervals, we can have a table. One is here time, here concentration of A. T0 concentration of A0. T1 concentration of A1, T2 concentration of A2, T3 concentration of A3. So several kinetic data are obtained by means of direct experiment. So this data putting here, we can draw a graph. Here T is independent variables, and here left hand side is ln concentration of A divided by concentration of B naught minus concentration of A naught minus concentration of A. This is plotted in the y-axis. So the left hand side is plotted along this y-axis, and T is plotted along this x-axis. T is independent variables and this part is dependent, as A depends on the value of T. So we have a straight line having some intercept. The intercept will give you here 0. Intercept will give you ln A naught by B naught, and the slope equal to, suppose this is tan theta, this is theta, so slope is tan theta, and this one equal to K2 into concentration of A naught minus concentration of B naught. And from this slope you can find out the value of K2. So this is the experimental determination of rate constant K2 for this second order reactions, which is very important. For the reaction, K2 remains constant at a given temperature. Then fourth one. Some example. One example I can give here, that is alkaline hydrolysis of ester. Alkaline hydrolysis of ester. Suppose CH3, COO, C2H5 have been taken as the ester, and say alkali sodium hydroxide, and giving you the sodium acetate plus ethyl alcohol. All are in aqueous medium, so volume of this solution already remains constant. So in this case, say alkaline hydrolysis of ester, it is also called saponification reaction. Saponification means the soaps are prepared by alkaline hydrolysis of desaccharides of long chain fatty acids. So it is called saponification reaction also. Now, initially, these are the known concentration, these are the known initial concentration when T equal to 0. This one is concentration of CH3, COO, C2H5, 0, and here it is sodium hydroxide, and this is 0 and 0. So initial concentration of these two have been taken, known, and they are mixed at a given temperature. Temperature have to be kept constant. Whenever temperature is changed, K2 will also change. Generally, when temperature will rise, K2 will also rise according to the generally, and it will follow the Arrhenius equation, which we shall deal in our later discussions, next discussions. And so now this is this sodium hydroxide. This sodium hydroxide, as the reaction goes on, the concentration of sodium hydroxide will decrease. As the time increases, so concentration of sodium hydroxide will decrease. And the concentration of sodium hydroxide at different time intervals are determined by titrating adequate amount of the reaction mixture and with standard oxalic acid using phenolphthalein indicator. So adequate amount, say 10 ml or like that, have been pipetted out from this reaction mixture, added to an ice cold water, so that reaction has been stopped, freezing of reactions, and then the remaining sodium hydroxide is titrated by means of standard oxalic acid using the phenolphthalein indicator. So this is one bright example for this reaction where these two are not equal. So this is the kinetic of second order reaction of part 2, and next class will be the kinetic of second order reaction part 3, where another three features: half-life period, pseudo-unimolecular reaction, and how this rate equation is converted into the first into this second order reaction where these two are not equal, but whenever these two are equal, this rate equation, this integrated rate equation is not valid, since this one becomes a 0. So how this equation could be reduced to the integrated rate equation when these two are equal from here? This will also I shall discuss in my next part 3, and that will be sixth point of this chapter, of this topic. So thank you all for watching this video. Next day I will discuss the kinetics of second order reaction part 3. Thank you all.